Hello, this is section 4.2 for Calc AB, and today we're going to be talking about area. And I know that seems a little weird, but I promise it's going to be really fun. So we start off with actually a little bit of review with sigma notation, meaning summations. So of course, this is where you start. You start with the first, so you plug 1 in to your function here, and then you go all the way until you get to n, and then you add those together. And of course, you increase by integers as you're plugging those numbers in. So this is just a start with 1, you plug 1 in, you see you get 2, you plug 2 in, you get 4, plug 3, and then you stop when you get to that top number there, that n value up top. Then you're going to add all those terms together, and then that gives you the summation. So now be careful that it starts, you're used to it starting at 1, but that's not always the case. So just make sure in this case it starts at 7. So we plug 7 in first, then we plug 8, 9, 10, and you stop when you get to 11. Get all those values, add them together, and so forth. Okay. Now, there are some properties of summations that you might remember. If you have a constant or a scalar, you can move that out in front. If you've got two functions here being added or subtracted, you can break the summation up, just like with differentiation and integration. But here's the nice thing. Here we've got some nice formulas, but you have to make sure it starts at 1. In order to use these formulas, you need to make sure I is 1. But if ever it's a constant, you just multiply c by the number of terms. So c times n. If it's ever I, you can use this. You might remember doing this in geometry. We called it the handshake problem. But that's what this formula is. And then I squared, and then I cubed. And hopefully you're like, oh yeah, I've seen these before. So I kind of demonstrate down here, instead of having to plug 1 in, then 2, 3, 4, 5 into this polynomial, and then adding all those together, you can take advantage of the formulas. So I broke it up into 3 different summations, which is perfectly legal. Moved the scalars in front, the 2 and the 3. And then here now you've got the summation of I squared starting at 1. You can use the formula. Here's your I squared formula here. N being 5, so you can see I plugged in 5 times 5 plus 1, which is 6, and then so forth, got 11, and then all over 6. And here, so you can see that this summation of I squared was replaced by the formula. Oh, that's pretty nice. And then they did the same thing here. Replaced this summation of just I with its formula, n times n plus 1 over 2. And then in this case, it was just a number, so we used this formula, c times n, got 30. So if you've got it set up to use the formula, use it. But it has to start at 1. That's really important. And that's just another example. So I distributed, so I was able to get I cubed and I was able to take advantage of the formulas again. Okay? You need to practice those just to refresh. And you, of course, can do summations on your graphing calculators, so you'll want to explore that. And then this is just working backwards, starting from your addition here and then working backwards to write it in summation notation. So you guys can look through that. That should be pretty obvious. All right, and then now we're going to switch gears. This starts with 2 random topics, but then I promise we'll bring them together. So we talked about summations. Now we're going to talk about area of a plane region. So these are just some examples of where I graphed the function. In this case, 3 was a horizontal line. And then it said from 0 to 8, it created a rectangle. And then in order to find the area of that region, you use the area of a rectangle. So that's what we did. And then here in this case, we graphed 2x, which is this line here, and said from 0 to 4. So we have this region, which of course is a triangle. So we use the triangle formula, got the area of that region. In this case, it was a trapezoid. So we use the trapezoid formula, 1/2 base 1 plus base 2 times the height. And then this last one ended up being a semicircle. So the key thing is, all 4 of these, we had a formula to use. But the problem is, what if it's a function like this curve here, where we don't have a nice geometric formula that we can depend on? So that's where, if we want to get the area under this region here from A to B, we kind of have to use our geometry formulas to at least give an estimate. We don't have a way of finding that area yet. So what we are demonstrating here is, well, you could do, we call these lower sums, because notice with each rectangle you're picking the lower of the two heights. And then over here, same rectangles, but now we're picking the side that has the higher. So we call these upper sums. See how it picks the higher of the two sides of the rectangle each time to give the upper estimate. And then of course you can imagine if we then take both of these and average them together, you're getting a better estimate of the area under the curve. Okay, so here's an example. Use 4 rectangles to approximate the area of the region bounded by 8 minus x squared. So go ahead, I went ahead and gave you the curve. So graph that on your notes. And then from 0 to 2. They didn't indicate what the base length of each rectangle needs to be, so I would just make them the same to keep life simple. So I just made the base length 1/2. So if you notice, upper minus lower, and then divide it by the number of rectangles, that's giving us the change in x. We say b minus a over n. That's a formula that'll pop up later. Okay, but it never said that the rectangles had to be the same base length. So you could do whatever you want as long as you have 4 rectangles. Okay, so for each rectangle to do an upper, now notice looking at your 2 lengths here, which one will give you the higher of the 2 heights? And of course that's going to be at 0. Okay, and then same thing with the next rectangle. It's going to be this time at 0.5. So that's what's happening here. This is the base length of each rectangle, and this is giving us the height of each rectangle. So that first one we used, x at 0, then x at 1/2, then the next rectangle will be x of 1, x equaling 1, and then the last one will be the 1.5. And notice that gives us our 4 rectangles. So we're using what we're going to call the left side. Gives us the upper estimate. So then you just plug those numbers into your function to get the heights and then add them together, and that gives us the approximate area using those rectangles. Now for the lower, you'll want to pick the right side of each rectangle because it's always a decreasing function. So we went with the right side this time. So notice I went ahead and started all the way to the right with this last rectangle. And that gave us the lower estimate of each rectangle, and then we added them together. And you notice you get 12.25 over here. That was our lower estimate, and our upper being 14.25. And then if you average those, you're getting a pretty good estimation of the area under the curve. All right, now we did the same thing over here. Find an upper and lower estimate for the region bounded by the graph. So I went ahead and sketched that parabola there. And the x-axis between 0 and 2. Never did it indicate how many rectangles we had to use. So I just did 2. Now that's not going to be a very good estimate, but there it is. So I did an upper, and I made the base length of each rectangle 1. So I did the upper, and you can see that's going to be the right for each one of these. And then the lower ended up being the left. Now, with both of these, it was consistent. The upper was always the left side of the rectangle, the lower always with the right. But if your function changes from increasing to decreasing, that's going to change. So notice when it's increasing, your lower estimate's the left, but as soon as it starts to decrease, now the lower is going to be the right side of the rectangle. So you have to be a little bit careful. When it says upper or lower, you'll have to be very vigilant about if the function's increasing or decreasing, and you'll have to be careful with that. All right, so here's where we're going to marry the 2 concepts together. So we talked about summations at the beginning of the notes when we're adding as you were plugging your lower bound in, you're adding your function values together. Now in this case, we're going to take advantage of the rectangles. So we're going to add a bunch of rectangles together. So if you ignore the limit and summation notation for a second, if you look, it's just f of c sub I times the change in x. That's the area of one rectangle right there. But then if you put this notation in front, now you're adding as many rectangles as you want. But then here comes the calculus magic. If you put the limit notation in front as n approaches infinity, now all of a sudden you're adding infinitely many rectangles together and getting the area under the curve. Now it's not the exact area, but it is immeasurably close. So that's pretty amazing. So this is kind of the magic that gives us the area under the curve. Okay, so let's try to apply this concept. And we'll go a little more in detail with this stuff in class, all right? But find the area of the region bounded by the graph. So now we're actually going to truly try to get the exact area under that curve from 0 to 1. Okay, so we got to get this all set up. So notice my limit as n approaches infinity, the summation from 1 to n of f of, okay, we got to figure out what this, we got to figure out the c sub I and the change in x. Now the change in x is really easy. That's just b minus a over n. So that's, you're going to take your upper bound minus your lower bound, 0 over n. You get 1 over n. That's our change in x. Okay, now this is really important. Remember, I made a really big deal about this having to be x equals 1 in order to use those nice little formulas. So when you think about this, we don't want to start, let me scroll back up here. We don't want to start here at 0. We want to start at the next, we want to start here. So it's going to be starting at 1, not at I equals 0. So when I come down here, we're going to want to always use the right side of the rectangles when we do this formula. So it's always going to be your lower bound plus I times the change in x. That will get us to the right side. Because notice if you do that, 0, here it's better demonstrated over here. So to start with the right, it's going to be our lower bound 0 plus the change in x. That gets us to 0.5, and that's this height of the rectangle using the right side. So I know that's a little confusing, but we always use the right side when we do this formula so that we can use I equals 1. So we can use the formulas. So that's where I'm getting the c sub I. That's the lower bound plus I times the change in x, and you get I over n. And that's what we're going to put in for c sub I. Now from there, you go into solve mode. So in this case, we plugged I over n into our function, 2x squared here. And then the 2 and the n's, all that, those are scalars. Those can all be moved in front of the summation. So that's what I did. And now I've got this beautiful summation of I squared. I can use the formula, which I did. That's what's here. Now don't move that n cubed down in front of the limit, because notice that's what you're doing. That's what your limit's with respect to. So you can't move that in front. But once you've done the formula, then you simplified it down, and then we were able to find that limit. And of course, the degrees are the same, so it's the leading coefficients, and that's your answer. Yay. Isn't that cool? And that's the area under the curve. Okay. All right, now I'm going to talk you through one more here. So find the area of the region bounded by the graph, f of y equals y cubed over the y-axis. Okay, so that's what's going on. So here's our formula. You've got to fill in the c sub I and the change in y in this case, because we're going along the y-axis. All right, so b minus a over n, so your upper minus lower over n, and then your c sub I, that's your lower bound, which is 0, plus your I times the 1 over n, your change in y. So we plugged it in, then plug your I over n into your formula, move the n in front of your summations, plug your formula in, and yeah, there it goes. So once you get it set up, once you get your c sub I and your change of x, or change of y in this case, you're golden. You plug those in, plug the I over n into your formula, and go from there. Okay. Now, another way, so we talked about using upper, lower, or technically left and right, which we'll talk about that in the next section. There's another way to do it. You can also use the midpoint rule. And it just takes once you've got your rectangles established, then you're going to just use the midpoint of each rectangle. So that's what I'm showing you here. So once we got our change in x, which was just 1, then we went and used the middle of each rectangle to plug into our function to get the height. Okay. All right, and then down here, this is something for you to look at, but it's just another example of me demonstrating that limit process to find the area under the curve. Okay. All right, you need to practice this, but let me know if you have any questions. Thanks.